Okay, so this is still section 2.1, and we're looking at matrix multiplication. Now, before we do matrix multiplication, I want to do something that might be review for some of you, and some of you maybe haven't seen it before. And that's this idea called a dot product. I think it kind of comes in handy when learning matrix multiplication. So a dot product, okay, so let's look at how that works. So suppose I have two vectors. We have x, and that is, say, x1, x2, x3, and y, and that's y1, y2, y3. It could be any length here on these. And generally, just for dot product, we are just talking about vectors. And so technically, I could have one going across, one vector going across, one going down. And that, you know, at some point when we're working on some applications of matrix arithmetic and so forth, it absolutely matters how I'm thinking of my vector, whether it's going across as a single row or down as a single column. But for just the dot product definition, actually, I don't have to worry about that. Now, so what is the dot product? Well, it's called the dot product because our notation for it is a dot. And so you got to be a little careful with that dot now because, right, you know, I might say something like 2.3 equals 6, right? You know, because 2 times 3 is 6. Well, actually, that's okay. It will still fit this definition if I had 1 by 1 vectors. It still would work this way. But let me write out what this is. We go element-wise with our products, and then we add those together. So you get x1 times y1 plus x2 times y2 plus x3 times y3. So the important thing to realize here is a dot product between two vectors creates a scalar. Okay, this is a real number. So that dot product is that. Now, why the dot product? Well, when we look at matrix multiplication, okay, it is not what one would tend to expect. There is a matrix multiplication defined the way one might expect multiplication to be defined, but it's not very well. It's not useful to us. I mean, it definitely comes in handy in some situations, but typically we don't use it. And so what do we use? We use this definition because it comes up. Okay, it's extremely useful, this particular definition. Now, so why did I mention the dot product? Well, because if I take A times B as matrix multiplication, it's handy to think of A as rows and B as columns. Columns. Okay, and the reason is, for the definition, if I look at something like this, and I'm going to take A as rows, and let's say it has 3 rows. So I'm going to call this A1, A2, and A3, those rows. And I have 3 columns here. Well, actually, let's go with 2 columns. B1 and B2. Then when I multiply these 2 matrices together, the answer is the matrix, and actually I should put lines over these because those are vectors. The answer is A1 dot B1. That's the 1, 1 entry, row 1, column 1. Oh, row 1, column 1. Hey, I can maybe remember this. Okay, then row 1, column 2 is A1, B2 dotted. Now, row 2 is the row 2 from A, and the first column is the column from B. So we get A2 dot B1, and then A2 dot B2. And then A3 dot B1 and A3 dot B2. Now, what we see from this is if A is M by K and B is K by N. Notice number of columns here in A. I didn't show you the columns, right? But the number of columns there in A and the number of rows here in B, I didn't show you how many rows, but they have to be equal. Now, why? Well, because we define this matrix multiplication as these dot products here, and to do the dot product, right, back here at dot product, these 2 vectors have to be the same length. And so the length of that row there has to be the same as the length of that column in B. So the length of the rows in A is the same as the length of the columns in B. That's why we have this K here. And so if we have that, then the product AB, so maybe I'll say C is equal to AB, is M by N. Okay, the number of rows of A and the number of columns of B. So that is matrix multiplication. And so suppose we have A is, whoops, not sure, I just made it real big or something. 1, 1, 0, minus 1, 2, and 3, and say 1, 3, and negative 1. And B is, now I better have 3 rows in B because I have 3 columns in A. But now B, I could have that be something like 2, 1, negative 1, and 0, 3, 0. Something along those lines. Sorry. Making you dizzy maybe. And now if I take A times B, okay, that's my 1, 1, 0, negative 1, 2, 3, 1, 3, negative 1. times 2, 1, negative 1, 0, 3, 0. And the answer is, well, I'll leave lots of room to do this, I hope. I have enough room. But see, I look across the rows here, and I look down the columns here, and so I end up with, and of course I made it hard to see what my number was. I'll look back up there. I get 1 times 2. Now I'm using parentheses just to not use a dot, because the overall thing is the dot product here. And then plus 1 times 1, and then 0 times negative 1. And then I do that first row and the second column. Now that one I'll shorten up a little bit because I've got some zeros, so I'll get a 0 plus 3 times 1, so I'll write the 1 times 3, and then plus 0. Now for the second row, I have my minus 1, 2, and 3. I put some extra stuff in there, so I'll get rid of that so it's not quite as confusing, hopefully. And now, so I take my negative 1 times that same 2 I did before, plus a 2 times that 1 here, in the first column of B, and then plus, oops, I forgot a plus sign up there, plus 3 times negative 1. So notice the second numbers in both, in the first, the corner item here, first column, or first row, first column, and then second row, first column. The second numbers involved in this dot product are always the same because they're the same column of B. And then now I'll get my 0 again, just because I don't have much room here. I'll do that, and then the 2 times 3, and then another 0. And then finally the third row, I get a 1 times the 2 plus 3 times the 1, and plus negative 1 times negative 1, and then 0 plus 3 times 3, and plus a 0. And so my product is a matrix that's 3 rows by 2 columns, and I get, let's see, 2 plus 3 times 0, or plus 0, 2 plus 1 is 3, so yeah, 3. Then I get a 3 here, and then negative 1 times 2 and a 2 times 1. Oh, well, they cancel each other out, and then 3 times negative 1 is a negative 3, and 2 times 3 there is 6, and then 1 times 2 and 3 times 1, that makes a 5, and negative 1 times negative 1 is 1, so that makes 6. And then 0 and 3 times 3 is 9, and another 0. And so there's my product. Okay, that you want to practice a lot with matrix products, and just do a lot of practice. Okay, a very good idea there. You need to build that motor memory, doing it with all different sizes of matrices and so forth. And now you can do it as a summation, but right now I'm not going to worry about the summation stuff, the summation notation. Let's just worry about being able to do the matrix multiplication. Okay, so there's just the technique of matrix multiplication. Practice it a lot.